reflection and transmission. So we're going to talk about reflection at a boundary. Now, a boundary can be when a string hits a fixed object or just a different string. So the initial pulse is called the incident pulse. That means it's incoming. The energy that bounces back is called the reflected pulse. Just like if you look at the mirror, the light that's reflected back is your reflection. All right, as we saw during our lab, some energy is transmitted to the pole. We'll talk about transmissions in a second. So, a fixed end reflection is what you guys were looking at in your lab. All right, so we'll talk about with a fixed end first. So, the reflected pulse is inverted. That means it's the same shape but upside down. We're going to pretend like this is a perfect world where we don't really get any energy lost to the pole in this particular case. The wave speed and the wavelength do not change when it's reflected. In real life strings, yes, the energy eventually dissipates. All right, so you might see that in a question, but mathematically and graphically, we're usually going to stick with the fact that it's the same. So you can see in this picture the incident pulse is above the string and the inverted reflected pulse is now below the string. All right, so what if the other end was free to move? In that case, the reflected pulse is not inverted. So say instead of tying it to the pole, we had put a ring around the pole that was allowed to move up and down. Now you're going to get a reflected pulse that is identical to the incident pulse, just going the opposite direction. So now we have to talk about transmission. So the energy that is transferred to the pole, or if to another string, would be called the transmission. So if I connected two slinkies of different densities, I'd actually get a combination of reflection and transmission, and you would see both a reflected pulse and a transmitted pulse. So let's look at that scenario, because that's more interesting. So if I went from less dense to more dense, and you can see the boundary there in the middle, all right, boundary conditions are very important when you want to start graphically and numerically looking at these in later physics classes. So just like if I have a fixed end, the reflected pulse is inverted, all right? So a string hitting a pole, the pole is more dense, so if that string can't move, the reflected pulse is inverted. The transmitted pulse moves slower because it's harder to move that denser string. All right, and therefore you have a smaller wavelength. The frequency stays the same though. The reflected pulse has the same speed and wavelength as the incident pulse, but it's going to have less amplitude because it has less energy. We'll talk about the relationship between energy and amplitude in more detail later on. All right, and here's a picture of what this would look like. All right, now we're going to look at going from more to less dense. So now the transmitted pulse is going to travel faster, all right, because it's going to be easier to move that less dense medium. So a faster wave speed, but the same frequency is going to equate to a larger wavelength. The reflected pulse, again, is going to have the same speed because it's in the same medium, all right, and wavelength as the incident pulse. Again, less amplitude. And here's what that looks like. Here, you'll notice that neither pulse is inverted. They're both above the string if it started above the string. A couple of quick rules of thumb to talk about anything that happens at a boundary. If you stay in the same medium, you will keep the same wave speed. The wave speed is a property of the medium, not the wave itself. The frequency of the wave is what is going to determine the wavelength in that specific medium. And if I have the same wave and I change mediums, I will have the same frequency. That's a property of the wave. The medium is what determines the wave speed, all right? And then based off of our wave equation that we got yesterday, that will actually determine the wavelength of that particular wave in that medium.